Kupin, who will talk about subtraction-division games, patterns, and self-similarity.
So again, for those of you who don't know me, my name is Beth Kupin. I'm a grad student here at Rutgers. I want to talk about a class of two-player combinatorial games that I call subtraction-division games. So first I want to start just by talking about the game itself. I think of each of these games as having three parameters, A, B, and N. It's a two-player game. Both players are competing to say the number 1. They start at N, and each player on his or her turn can either subtract A from the total or divide by B. Those are our two parameters. When we divide by B, if there's some kind of remainder, if it doesn't divide evenly, we will round up. So here's an example of sort of a simple game. We start at N equals 8. Player 1 decides to subtract 1 from the total. Player 2 decides to divide by 2. Right? 7 over 2 is 3 halves. Of course, we have to round up, so the total is now 4. Round 2, player 1 decides to subtract 1. We're at 3. Player 2 decides to subtract 1. 3 minus 1 is 2. Of course, player 2 is sort of in trouble here, right? If player 2 had decided to divide, right, we would have instead divided 3 by 2, gotten 1/2, rounded up, right? Player 2, even though they have 2 moves, really only has 1 move at this point. And of course, once the total is at 2, player 1 subtracts 1 and wins. And so we can ask ourselves some questions. Did player 1 have to win? Could player 2 have done something else? And really, the main question that we're interested in is if we have these 3 parameters that are describing some game, is there a winning strategy for the first player? No matter what the second player does, can the first player always win? And if there isn't a winning strategy for the first player, then there has to be one for the second player. So this is the game that we're going to be talking about throughout the whole talk. This is what I think of as the general subtraction-division game. So a quick overview. Here again is the main question. We're looking at games with these 3 parameters. We're going to start by really talking about this simple version where we just subtract 1 and divide by 2. We're going to build up some results there, and then we're going to look at generalizing it a couple different ways. We're going to generalize it to dividing by other even numbers, and then eventually to subtracting other numbers as well. Okay, so starting with the game subtract 1, divide by 2. One of our main tools is Sprague-Grundy analysis. And this is a fairly standard thing if you've worked in combinatorial games. Here's a digraph that represents our game when we start at 8. Right? It has a node for every potential state, and the arrows just tell us what our moves are. Right? If we start at 8, we can either subtract 1, that brings us down to 7, so we have an arrow there, or we could divide by 2. So once we have this graph written down, we're going to assign each state in the game a number that's going to be its Sprague-Grundy value. And we're going to start by assigning sort of the end state value 0. From there, we can recursively define the rest of these values. The label of every other node is going to be the smallest non-negative value, smallest non-negative integer, I should say, that doesn't appear as the label of one of its outneighbors. So if I want to assign a label to 2, state 2 depends on state 1, right? The label at state 1 is 0. So the label at 2 is going to be the max, the minimum excluded value, just over the set 0, smallest integer that doesn't appear as 1. Similarly, state 3, we set at state 3, even though in theory we have 2 moves, there's really sort of effectively only 1 move. We can only move to state 2. The smallest non-negative integer that doesn't appear as a label is 0 in this case. Moving on, this is sort of the first interesting case. At 4, for the first time, we really do have 2 distinct moves. We could either move to a state with label 0 or label 1. The smallest value that doesn't appear is 2. And we can keep going, and keep going, and keep going. Right? And eventually we can label everything in the game. One thing I want to point out, because we have limited out degree, right? We only have 2 moves from every state, we're never going to get a Sprague-Grundy value larger than 2. It's always going to be 0, 1, or 2. No 3s, no 4s. Why is this helpful? Well, if a state has Sprague-Grundy value 0, then it's a first player loss. And if it has Sprague-Grundy value non-zero, either 1 or 2, it's a first player win. And so even though we're giving it, or because we're giving it this mathematical structure of defining the Sprague-Grundy value with MEX, we have some sort of algebraic tools that we can use, but this really is going to have the information that we want it to. By analyzing the Sprague-Grundy sequence, we really can get to whether something is a first player win or a first player loss. Okay? And it's not too hard to see why this is true, right? It's certainly true for state 2. 2 is a win for first player, right, and has a non-zero value. And you can just look at it, what it means for a node to be a win. Right? It's a win if you can move to something that's a loss. That means you hand your opponent a losing position. And it's a loss if everything you do moves your opponent to a winning position. Right? And that's essentially exactly the same as our definition for what it means for something to have a 0 value or a non-zero Sprague-Grundy value. So this really does line up. So once we have this, we want to start looking at some data. So here's the first few terms. This is almost 200 terms of the sequence that I call SG sub 1, 2 of n, right? Where the value of the nth term is the Sprague-Grundy value of this game. We'd like to start recognizing some patterns, ideally. When we first look at it, we don't maybe see any. These are blocks of width 25. It helps a little bit if I rewrite it into blocks of width 24. Now, maybe we start seeing some patterns. One of the things that I noticed is we start getting these columns of all zeros. And these are the Sprague-Grundy value of 1 to n, where n is 4k plus 3, right? And n is equivalent to 3 mod 4. These games always seem to be losses for the first player. We also might notice that we have some columns that are all non-zero. Right? They can be 1s or 2s. Both 1s and 2s are wins for first player. But we have no losses in those columns. And that's every even column appears to be non-zero. Ideally, we'd like to find a pattern in the final residue class, right? Look at these ones that are odd but equivalent to 1 mod 4. Nothing jumps out, at least to me, when I first started looking at this. But I want to go through and actually justify the patterns that we saw on the first two, right? That n is 4k plus 3 is all 0, and we also have these columns of non-zero terms. We have to be a little careful when we look at data. 200 terms is actually not a whole lot, right? We want some kind of justification that this really does keep going. This isn't a fluke just of some initial conditions. It's not hard to do. I think it's worth going through. We're going to start actually with the second claim, proving that if n is even, right, then the Sprague-Grundy value is going to be non-zero. We can go by induction on k. I have the Sprague-Grundy value of 2k written out sort of on the top as its definition in terms of MEX, but sort of in the middle there I have the underlying digraph. And the words sort of and symbols get very complicated, but if you follow the digraph, it shouldn't be too bad to look at. So we're going by induction. We'd like to show that the value at 2k is non-zero. We get to assume that the value at 2k minus 2 is non-zero. One thing that could happen is that the value at k is 0. Well, if that happens, then the value at 2k can't be 0. The value at 2k is the MEX over the things that appear as labels of things that it depends on. 0 is going to show up in that set, which means that it isn't going to be excluded. We can't possibly have that. However, if k is non-zero, then if we look at 2k minus 1, 2k minus 1, the Sprague-Grundy value there is going to be the MEX over a set of size 2, and both elements are going to be non-zero. So even though we don't know what those values are, we know that the value at 2k minus 1 has to be 0. 0 isn't showing up in the set. It's going to be the smallest excluded value. But of course, if the value at 2k minus 1 is 0, then we get again that the value at 2k is non-zero. So no matter what, we've set this in motion. So much for the second pattern.
Using the law of excluded middle.
Yes, using the law.
Okay,
Yes. The second, or I guess this is really the first one on the other side, that when n is 4k plus 3 is all 0, this follows pretty straightforwardly once we know that the Sprague-Grundy value of any even number is going to be non-zero. If a term has n equals 4k plus 3, the two things that it's going to depend on are both going to be even, so they're both going to have a non-zero Sprague-Grundy value. The value of 4k plus 3 has to be 0. So these really do happen. This isn't just some weird trick of the data in the first 200 terms. These really are going to continue throughout the whole game. I want to talk a little bit about this other residue class mod 4. We noticed there wasn't a nice pattern. We couldn't say that it was all zeros or all non-zeros. And we see this kind of reflected looking at what the Sprague-Grundy value of 4k plus 1 really is going to be. And it depends on something that's even. That's going to have a non-zero value. And then it depends on something that's odd. It depends on 2k plus 1. Because of course, if we take 4k plus 1, divide by 2, we'll have to round up. We get to 2k plus 1. So if we happen to know that 2k plus 1 was equivalent to 3 mod 4, then we would be set, right? We just showed that if 2k plus 1 is equivalent to 3 mod 4, then that's going to be 0. We would know exactly what's happening at 4k plus 1. So that's sort of one option. Doesn't always happen like that, though. So really what we're going to have to do when we have a number in this residue class, we're going to have to keep doing this divide by 2 and round up until eventually we get to something that's equivalent to 3 mod 4. Unless we start with 1, as long as we start with something like 5, we will eventually hit a number like this. Right? And then sort of down at the sort of absolute lower right of this tree, we're going to hit something that finally has Sprague-Grundy value 0, and we'll be able to count back up. This seems a little bit dire, right? This doesn't seem a whole lot better than just looking at the recursive definition. But in fact, it's not that bad. We can actually write down a closed formula for whether or not this is going to be 0 or non-zero. And so we're going to take our number that's 4k plus 1, and we're going to write it down in binary. Because it's equivalent to, because it equals 4k plus 1, we know the last two digits are going to be 0, 1. So there's going to be some block of zeros, of length at least 1, that occurs before the final 1. Right? Some set of them. Right? And every time we divide by 2 and round up, we're essentially deleting one of those zeros. Our number gets smaller because we're dividing by 2. And what's happening to the binary representation is one of the zeros is going away. So the length of that zero, that block of zeros, is exactly how many levels down we're going to have to look in the tree. Right? Eventually, once we get rid of all of our zeros, we'll get to a number that ends 1, 1. Right? That, of course, is going to be equivalent to 3 mod 4. And really, all that matters is the parity of the number of levels we've looked. Right? Whether or not we're 0 or non-zero is going to alternate as we count back up. So if that's an odd block of zeros, we're going to have a win. That is a non-zero Sprague-Grundy value. And if it's an even block of zeros, we're going to have a loss. So a Sprague-Grundy value of 0. So by looking at it in binary, we're actually able to get a nice closed form for these things. Even though we can't say it's all 0, it's all non-zero, just by looking at n, can very quickly compute, is this going to be a win or a loss? All right, so the other thing that I wanted to look at is we have all of this information in the Sprague-Grundy sequence. We have sort of more information in the Sprague-Grundy sequence than we do just in the pattern of wins and losses. As you start to look at the data just of that sequence, we notice some interesting patterns. Oh, but I'd better say first, I didn't prove this. Frankel proved it very recently, that this Sprague-Grundy sequence is aperiodic. We never get to a place where it starts repeating. But we can still have some very interesting patterns. Here's a bunch of them.
Doesn't it follow from your result? Is that periodic?
That it's aperiodic?
Can you get a contradiction if it is periodic?
I believe so.
I think it's correlative.
Yeah. I believe so. And it's also very natural in some sense because we're dividing. We wouldn't expect it to be periodic, right? If we had some period, depends on certain things by division, right? We go out to the next one, it doesn't just look back.
Obvious.
Yeah,
I think it also follows as corollary.
Yeah, I think so. So the theme here, right, we're looking at certain residue classes mod 16, right, those are our indices, and we're able to compare something like SG of 16n, picking out just every 16th term. We're able to say that the term by term, that's equal to looking at every fourth term. And so this isn't obvious to me a priori, right? I discovered this experimentally. And we're really relating a fairly sparse sequence to a less sparse sequence, right? We're defining it in terms of things that are smaller. I discovered actually these first two, the SG of 16n equals SG of 4n, 16n plus 1 equals 4n plus 1, and I was curious to see if the pattern kept going, and I was really surprised to see that it did. And in fact, we can get all of the residue classes mod 16 to appear as some residue class modulo some smaller power of 2. Right? They're not all power 4, right? Some are 8. And we also do get some of them appearing as all zeros, right? Of course, we know that if it's 4n plus 3, it's all zeros. Of course, 16n plus 3 is going to be all zeros. And once you sort of get the data for these, once you sort of get a sense that something like this might be true, they're actually not too bad to go back and prove the induction individually. There's sort of a big underlying question here, which is what's really going on? What type of framework is really going to describe this type of self-similarity? What kind of a pattern is this? And fortunately, there is a very nice, succinct answer to that question, which is k-regularity. So we say that a sequence is k-regular if, when we look at the residue class as modulo some large power of k, right? When we look at f of n times k to the a plus I, right? So some residue class, we can write that as a linear combination of residue classes modulo smaller powers of k. Right? And that's exactly what we had here. Let me just flip back for a second. Right? We had residue classes modulo large powers of 2, modulo 16, all in terms of residue classes modulo small powers of 2. So our sequence is 2 regular. And of course, this definition is actually slightly more general. This allows for linear combinations of sequences. Right? And what I found is actually sort of exact equalities, but it still fits into this, right? A linear combination of length 1 is still a linear combination. There's an interesting result in some of the literature about regularity, which says that if you have a sequence that's k-regular and it only takes on a finite number of values, if it's sort of a bounded sequence, then it's also k-automatic. And it has this really nice tie-in to computer science. If it's k-automatic, then there's a discrete finite automaton that can tell you the nth term in the sequence. I'm not going to talk about exactly what a discrete finite automaton is, but if you don't like those words, just think about it as a decision tree. So here's a little example. We've actually proven something much stronger, right? We've proved that the whole sequence is 2 automatic. But here, we can just check that the win-loss sequence of the game 1 to n is 2 automatic. So we start, right, we're given n in binary. We're going to try and compute whether it's a win or a loss. Right, we start with the least significant digit. We know if we input 0 as the least significant digit, it's even. We've checked that that's always a win. Right? So right away, we can classify those. Right? If it's an odd number, well, we check the next most significant digit. If that's a 1, then it's a loss. Right? That's equivalent to 3 mod 4. And finally, so I'm here, right? If our least significant digit was a 1, our second significant digit was a 0, right? Then we know that it's 1 mod 4. Well then, as long as we have zeros, we're just going to keep bouncing around back and forth between the state 2 and state 3. That's really just keeping track of the parity of that block of zeros. And once that block of zeros ends and we know whether it's an even or odd, we can say if it's a win or if it's a loss. Right? So this is the actual decision tree that sort of witnesses to the fact that our win-loss sequence really is 2 automatic. When we talk about a discrete finite automaton, we're talking about something like this, potentially much more complicated, but memoryless and just works on the base K representation.
So sorry. So what do you call it? It's a tree? There seems to be loops.
Yeah, you're right. So I meant the word decision tree to be fairly vague. You're right. This is not a tree. Okay. You could, if you wanted, you could rewrite it to have a lot more states and get rid of that loop.
Okay.
No, that's a very good point. Yeah, and so again, just as a reminder, what we've shown is not just that the win-loss sequence is 2 automatic, but the whole thing, right? Whether it's a 1, whether it's a 2, there's some discrete finite automaton that will tell us all of that information. So here's where I feel like we are. We've noticed these things about the game 1 to n. We've been able to say that certain residue classes mod 4 are either all wins or all losses. We don't know about 4k plus 1, right? But 4k plus 2 is a win, 4k plus 3 is a loss, 4k plus 4 is a win. Right? And we've shown that this whole Sprague-Grundy sequence is 2 automatic. And so these two ideas that we're going to want to take and generalize to start talking about dividing by other numbers. Okay. Are there any questions before I go further? Okay. These are the things that I'm particularly interested in. All right. So again, as we start talking about looking at other sort of variations on this game, in my mind, the first thing that we should do is start looking at some data. Here are two sequences, one with subtract 1 divided by 4, the other one with subtract 1 divided by 6. And we do start to notice some patterns here, and eventually you will too if you sort of look at it long enough. I'm going to highlight some of them. One of the things that we see that we didn't see before is that we have these blocks of length 2D where the Sprague-Grundy values just alternate. Right? We go 0, 2, 0, 2, right? Or here when we divide by 6, we now have blocks of length 6 where all we're doing is alternating. Right? So that's kind of interesting. We also notice some similar things about the columns. Right? I didn't highlight them, but if you check all of the columns that are sort of an even index, they're all going to be non-zero. Right? And in addition, we notice some columns that are all 0. And these are the ones that have sort of particular indices modulo 4D now. And again, right, this is only a little bit of the data. This is actually only 2 versions of the game. We'd like to say that this is true no matter what even number that we're dividing by. So we'd better go through and give a slightly more general justification of these facts. So you believe me that this isn't just special about 4 and 6, that if I subtract 1 and I divide by 2034, we really do get the same behavior showing up. So the alternation, the fact that we get these blocks that alternate, is fairly easy to explain. Right? If every block of length 2D, when we do this division step, when we divide by 2D and round up, that means that a whole block of length 2D is all getting funneled to the same smaller state. Right? Here you can see 40k, all the way down to 40k minus 2d minus 1, all depend on 2k. Well, 2k has some Sprague-Grundy value, right? 0, 1, or 2. There are only 3 Sprague-Grundy values available. Right? So in that block of length 2d, one of them's already been used up. Okay? So we only have 2. We can't have neighboring ones be equal, so we have to alternate. So this alternation pattern is actually not that mysterious once we kind of look into it. It really will happen for all of the blocks. So in the interest of time, I'm not maybe going to spend a whole lot of time on proving that we still have that all of the even indices are non-zero and certain odd indices are always 0. It's in fact almost exactly the same inductive proof that we had for subtract 1 divide by 2. We're really not changing anything. But it's also really not a fluke, right? It is the same proof. It really does keep happening. So we could go through and check. Right? We would get that all of the even ones, again, are non-zero. And once we had that, it would follow that certain odd indices have to have 0 Sprague-Grundy values. It's actually the same. I'd also like to generalize this other piece of information that I had, right? With subtract 1 divided by 2, we were able to write down a lot of these sort of recurrence relationships, right? The SG of 16n was SG of 4n. Here, we'd like to do the same thing with powers of 2d. We can. It starts getting a little bit messier, but in fact, we really can. And one thing we see right away from this is that when we're just dividing by 2, we could just go up to 16. Which would sort of be equivalent to going up to 2d to the 4th. Now, though, as we look at a general value of d, we have to go a little bit higher. So I was able to show that as we go all the way out to 2d to the 7th, then we really do get every residue class mod 2 to the 7th in an equation like this. I'm not totally convinced that this is best possible. I'd be very surprised. Okay? But I do know that at least once we get out to 2 to the 7th, we're done. Right? We really can hit everything there. So as a result, of course, we get that the sequence is 2D regular. We get that it's 2D automatic. The sort of exact same things that we had for subtract 1, divide by 2, all still hold here. Just a little compare contrast. Most of this looks very much the same, right? Except instead of having something win, right, and something loss, each of those blocks has now been expanded, and we have this long kind of alternating pattern that we saw before. Something win, something win, something win, and then loss win, loss win, loss win. And I want to point out, it's maybe lost a little bit when I write it like this, but in this first set of 2D terms, every value that shows up as a win there is the same Sprague-Grundy value, right? If this first one's a 1, and the next one's a 1, they're all 1s. And ditto for the question marks, right? Whether it's a 0, 1, or 2, they're all the same in that block. And of course, the same in through here. We also get this corresponding result about being 2D automatic. So we're going to switch tacks a little bit at this point. We're going to talk about the Misere game. In general, you can talk about the Misere game kind of for any combinatorial game. It really just means that we're going to switch the win condition. And so if you wanted to play the Misere version of tic-tac-toe, instead of trying to get 3 symbols in a row, you would be trying to avoid 3 symbols in a row. Right here, if we look at the Misere game, for what we're actually doing, instead of trying to say the number 1, the players are now trying to avoid saying the number 1. But sort of mathematically, right, once we have it in this symbol notation with this Sprague-Grundy value, really just corresponds to changing the value at SG of 1 from 0 to 1. Right? Everything else is still defined recursively. Right? So everything depends on this first initial value, and we're just going to flip it. Just so you have a little bit of a reference for this question, I'm interested in trying to figure out what's going to change here, right? Does this cause a big change? Does this cause a small change? Here's some of the data. This is the Misere version now of subtract 1 divide by 2. And I was kind of blown away. Almost nothing actually changes. I was expecting sort of like everything to flip, right? Almost everything that had been a win to be a loss. And in fact, the opposite is true. So you can see we get a little bit of noise up here. This first term that's equivalent to 3 mod 4 that we would have expected to be 0 is actually a 1. But everything else, all of the other terms, are zeros. And in fact, if we looked at the even index terms, we'd have the same pattern. We'd have a little bit of noise right at the beginning, but for large enough values of n, it would actually settle down, and we'll get that all of the values at an even index are non-zero. So strangely enough, there's something about the structure of the game that keeps this type of pattern even when we switch the objective.
So you have the same strategy for doing it either way? Except for the end game?
So that's a good question. My feeling would be yes, right? If most of these values are going to change, are not going to change, rather, then your strategy is essentially a set of moves that says, well, I'm here, I want to move to something that's a losing position for my opponent. Right? And if most of those zeros haven't changed, then
only
yes.
the very end you have to.
Yeah. I do want to say, though, in the residue class that we weren't able to say sort of was all wins or all zeros, right? And the ones that are equivalent to 1 mod 4, there are an infinite number of terms that have swapped from being a zero to a non-zero, or sort of a win to a loss, and vice versa. So in some sense, we don't talk a whole lot about the explicit strategy. So it's possible that it would have to change for certain values. Certain things that you would have hoped would have been a 0 are now a non-zero. So yeah, sort of an interesting mix. In some sense, we do still get a big change. We do have an infinite set of values, but it's a fairly sparse infinite set of values. And we have more or less the same long-term behavior for some of these patterns that we care about.
Well, the same happens for NIM, the more basic game, right? The reverse NIM or inverse NIM or Misere NIM.
Right.
It's almost the same, except when you have singles, right? That's where
Right.
parity. So it's, I mean, yeah, it is surprising, but not that shockingly surprising.
Fair enough.
The name was already a big surprise.
Yeah. We can generalize this further, right? We don't have to just stop at changing the first value. We can change any finite prefix, right? We can change the first 10,000 values